In this video, we're going to run bivariate and multivariate regressions. To follow along, download and then open up the weather dataset that's in Blackboard under the Datasets and Codebooks tab along with the codebook. It's a fairly large dataset. It's basically county level voter turnout for each presidential election. And so your codebooks list the year, the election year, the state name, and the county name. And you see here in the SPSS file, you've got the 1992 election for a particular state, Alabama County Chambers. This is a little bit further down. You see it's cell number 124. So for the 1992 election in Chambers County, Alabama, turnout was 48.02% of the voting age population. In Chambers County, Alabama in 96, it decreased to 40.67%, and then in 2000, Chambers County, Alabama turnout percentage was 43.34%. So it's looking at the percent of individuals that come out and vote on election day in the presidential election years. Say we are interested in these turnout numbers. So turnout's an interval level variable, ranges from 0 to 100%, and we can run all kinds of models and test hypotheses. So let's make that our dependent variable, turnout, and there's a bunch of different independent variables we can use, but let's start with the bivariate case and say that we're interested in unemployment, which is estimated unemployment rate, on the effects of turnout. To run the bivariate regression, you go Analyze, Regression, Linear, and from a previous video I had these already in here, but we'll reset it and make sure it looks like what you've got on your screen. So the dependent is our dependent variable, and we wanted that to be the turnout, so move turnout over. And the estimated unemployment rate or unemployment rate, we want that to be our independent variable, so move that over. Click OK, and the output will give you a bivariate regression. The first table to look at is the model summary, the adjusted R-squared value. The adjusted R-squared value is 0.001. Move the decimal place over 2 spots, and the way to interpret it then is that 0.1% of the variation in turnout, the dependent variable, can be explained by the independent variable, which is unemployment rate. So the unemployment rate explains 0.1% of county level turnout. So very low, and we'll see what happens when we add other variables in a second. In the coefficients box, you will need to interpret the beta coefficient on unemployment rate. We do the unstandardized coefficients under B, and it's a negative 0.162. It is significant at the 0.05, 0.01 level, so with the sig of 0.000, it's well above 99% significant. The way to interpret the coefficient or the effect of the unemployment rate on turnout is that, on average, ceteris paribus, a 1 unit increase in the estimated unemployment rate leads to a 0.162 unit negative sign on the beta, so that's a 0.162 unit decrease in turnout. To be more specific, unemployment rate is measured as a percentage, so a 1 unit increase in the unemployment rate is a 1% increase in unemployment. Turnout, its unit is in percent turnout, so it's also units are in terms of percentages. So the most specific interpretation would be, on average, ceteris paribus, a 1% increase in the estimated unemployment rate leads to a 0.162% decrease in turnout. Now we know that turnout is not only a function of unemployment rate, but all kinds of other variables. And if we go back to our code book, other important variables that we'll consider is the turnout lag variable, or the turnout in the previous presidential election. Counties that have high presidential election turnout for previous elections, that's probably a pretty good predictor of high turnout for the current election. So we should control for essentially voting history or the likelihood that voters are turning out in the past. Percent black could affect turnout along with farms per capita, median household income, and the data set was created to estimate the effect of rain and snow on turnout, so we'll add in rain and snow. The thing to pay attention to from our first model is what happens to the adjusted R-squared when we add other independent variables in, and what happens to the coefficients and potentially their significance. So to do the multivariate model, we just go analyze, regression, linear, and let's add in the variables that we think affect turnout. So we said turnout in previous presidential election, so move that over to the independent box. Estimated percent black population, move that over. Farms per capita, let's move that one over. Unemployment rate's already there, so let's add in a median household income at the county level. And then rain, GIS rainfall estimate, and GIS snowfall estimate. Click OK. And it will spit out new results. The adjusted R-squared has gone up, in fact substantially gone way up to 0.823, or 82.3% of the variation in the dependent variable, which is voter turnout, can be explained by all of the independent variables, or essentially our model predicts 82.3% of the variation in turnout. So 82.3% of the variation in turnout can be explained by all of our independent variables, which include estimated unemployment rate, turnout in previous election, estimated percent black population, farms per capita, median household income, rain, and snowfall. Remember, we had a coefficient on the unemployment rate in the first model was negative 0.162. It was significant. When we add in the other variables, it changes. It gets a little bit lower to a negative 0.094, or lower meaning closer to 0, or a lower effect. So now you would say, on average, ceteris paribus. Essentially, the ceteris paribus is saying that once we control for or take into consideration turnout in previous presidential election, percent black population, farms per capita, median household income, rainfall and snowfall, the average effect of a 1 unit increase on the unemployment rate is a 0.09 unit decrease in turnout. So on average, ceteris paribus, a 1% increase in the unemployment rate leads to a 0.094% decrease in turnout. It is still statistically significant, as are all the other variables. Whether or not you think 0.09% is substantively significant, well, that's up to debate. Some years, 0.09% decrease in turnout could swing an election a certain way. Other years, it doesn't matter. The rainfall estimate. How to interpret that? On average, ceteris paribus, a 1 unit increase in rainfall leads to a 1.076 unit decrease, the beta is negative, in turnout. So this suggests, if you want to interpret it really specifically, turnout's unit is in percentages, rainfall's unit is measured in inches of rain, so on average, ceteris paribus, a 1 inch increase in rainfall leads to a 1.076% decrease in turnout. It is statistically significant, and that 1% decline, 1.076% decline, is actually fairly large, so that's substantively pretty interesting. For some reason, it seems that snowfall increases turnout. On average, ceteris paribus, a 1 inch increase in snowfall leads to a 0.725% increase in turnout. That's something to be explained. Turnout in previous elections predicts turnout in the current election. Farms per capita, an additional farm per person in the county leads to a 10.805% increase in turnout. So you can see what multivariate regression does, why it's very important to include all theoretically interesting variables that could affect turnout within reason and within data limitations, because the coefficients, the betas, will change based upon the variables that you put in. In our bivariate case, the effect on unemployment rate was a negative 0.162. The effect's a little bit mustard. When you add in all the other variables, it goes to negative 0.094, so a smaller effect. So if you were to only include the one variable, unemployment rate, you would incorrectly estimate its effect on turnout. By adding the other variables, we are taking into consideration all of our other independent variables, and then we get the independent effect of unemployment rate. And in this case, a better estimate is 0.094 unit decrease in the turnout.